I'm really delighted to be in such a good school, escuela, and it's for me a pleasure. And I will talk a little bit about bridge design in seismic regions. As you all know, Portugal is we have mostly in the south, we have quite severe seismic regions. So I will talk a little bit about that. Well, just a small index. I'll start with an introduction. Bridge design in seismic regions, seismic actions and analysis. Well, we had two brilliant presentations previously, so I will skip a little bit this. Seismic devices for bridges and some examples of bridges built in seismic regions, and also some examples of tragic accidents. I left that for the end because I think we have to learn always from those accidents. Well, let's ask ChatGPT about bridge design in seismic regions. My son's father, just ask ChatGPT and we will have a presentation. No, it's not like that. And the answer is quite good, I must say. It touches everything. It's a critical task that requires careful consideration of various factors. Okay, seismic regions are areas prone to earthquakes, we know it, and can cause significant damage to bridges if they are not designed appropriately. That is the main point. And well, it involves understanding of the seismic characteristics of the region, of course, and selecting the appropriate materials, construction techniques, and ensuring that the bridge can withstand with the forces of the earthquake. Okay, critical task. It's not so critical. Let's see. It's if you have a good design, a good conception of the structure, it's not that critical. Well, so let's come back to bridge design, which involves, I must say, study. We have to study a lot. We have to see several examples of bridges well designed. We have in Spain a lot of brilliant designers, bridge designers. Some of them are seated here. Understanding of the structural and materials behavior. I put here a small example of an exercise that I always teach to my students. Some small portals with forces applied. What is the behavior of the portal? How this deforms? How are the flexural moments reaction? So this is very important to understand the simplest models, because bridges, most of them are simple models, and it's very important to understand how it behaves for vertical forces and also for horizontal forces. You have to have high dedication and commitment. It's really important. I put here a photo of my years from rugby player, and that taught me a lot about commitment, about dedication, and really to be a bridge designer, you have to dedicate quite a few hours on your project. Experience. This is a photo of Mr. Armando Rito on top of a bridge in Angola. I'm really honored, and it's really good for me to work together with him. He's 86 years old. And he still worked with high dedication and commitment. So it's very good for me to have him besides me working on our bridge projects. And of course, teamwork. You never know everything. You have some people more dedicated to some parts of the bridge design. You have other people dedicated to other parts. And so it's very important to create a good environment for a good teamwork for your projects. Well, in seismic regions, what to do differently? Not really much, just shake your mind like you are in an earthquake and think what you should do differently if you are designing a bridge on a seismic region or not. Some key factors that should be considered. Well, of course, if you have an earthquake, it could cause severe damage to your infrastructure, and you don't want that. So you have to take special attention to the safety and stability of the bridge. We are quite lucky in Europe to have the Euro codes. A lot of work has been done to achieve what we have nowadays in our codes, and that helps a lot the designers for their projects, because you don't have to think on most of the things that of the background of that documents, of that codes, but you have to think a lot on the conception of the bridge. That is, you could have the formulas and everything very well, but if the conception of the bridge is not good, you will not have a good result. Well, the selection of materials. Of course, it's important to have flexible materials and not brittle materials that will just collapse your bridge. And now, well, we have the reinforced concrete, of course, steel and composite materials to use on your designs. Construction techniques as base isolation on bridges. We don't put base isolation on the bottom of the piers, otherwise the bridge would fall easily, but you use it, well, in some types of bridge you can use, but normally base isolation on bridges on top of the piers, use some dissipation devices. But yeah, this point I consider really important to consider. No, this one. Consider simple and durable maintenance-free solutions. Nowadays, you have a wide range of seismic devices, but you should think on what's going to happen in the next years, decades, because you are designing a bridge for 100 years at least. So you should think a lot on the solutions that you put on your bridges. Local geological conditions, of course, you have to understand, you have to know where you're putting your bridge. If you have potential of liquefaction, is something that we really need to take care when you are designing a bridge with deep foundations on sand soils, mostly on sand soils, and proximity of active faults. Well, if you are designing a bridge on a bridge crossing a river, normally you have a fault more or less active. Appropriate seismic detailing. Yes, very important when you're designing mostly reinforced concrete bridges. You have to have really a good care on the detailing of the reinforcements and how to design your bridge to undergo the deformation without collapsing, because you accept the deformation, you accept the plastic hinges, but you don't accept that the bridge will collapse. Well, seismic action and analysis. As I told, we have the Euro code in Europe. In other countries, we have other codes. We have specific studies for specific locations, as in Mexico, for example. And you design the bridge for what the owner wants. He's the one who should say which seismic action, which importance class or consequence class that you should consider. And I put here this graphic, the accelerogram, where we can see the period of the structure. And we are lucky in bridges. Normally we have quite big natural periods, and we are staying in a range of accelerations lower. So you don't think on a bridge that should be very robust and very rigid to withstand with the seismic action, and then you have higher accelerations and higher forces on your bridge. So keep it flexible. Soil modeling with different scenarios. Yes, we should sometimes when you have mostly in deep foundations, we have to consider different scenarios, and with liquefaction, without liquefaction, and consider some differences on for example, the springs that you put to simulate the soil on your piles, and then you have to consider some lower and upper bounds to design your bridges. Well, let's skip this. Methods of analysis, we already heard a lot about this. Most of the times use the response spectrum method or a time history analysis, most common on bridges. Behavior factors, what should be considered or not. The displacement calculations, skip the behavior factor, because you really have to consider the real deformation, the real displacement, and the plastic hinges locations. Of course, on bridges, normally it's on the bottom of the piers that you need to consider the plastic hinges position, where you have the most, the biggest efforts. Well, seismic devices for bridges, we have a lot nowadays. You have outside most of the suppliers of seismic devices. I will not talk a lot about this, but what I can say is that you can use whatever you want to achieve your results. Mostly you can block some piers, you can free for seismic, or just block for the quick actions. And well, you have a lot, but you should, as I told before, should keep it simple and maintenance free. Well, some examples of bridges that we've designed in seismic regions, of course. This is one in the highway between Lisbon and Algarve. This was a design and build tender, and we have a big valley with low height, and deep foundations until 50 meters depth. We have potential of liquefaction in some parts of this valley, not everywhere, and this is the problem with these type of valleys. You have liquefaction here, you don't have liquefaction there, and then you have to consider all those scenarios in your calculations. And since we have this main bridge to cross the river, where we have a big span and we also have this pile pier solution on this with 2.5 diameter. But what is most interesting in this part is how to divide this bridge, because if you put a fully continuous bridge, you will have big displacements on the extremes, and that will conditionate a lot your conception. So here, what we divided this in the access viaduct in 3 stretches, plus the main bridge, and we could achieve a solution without special seismic devices, only using uni and multi and fixed bearings. How could we do this? Have a light deck, so low vibration masses. If you have a very heavy deck, you will have more problems. Flexible piers. There's a limit, of course, but you have to study what is the limit for the vertical forces and also for the seismic action. Low frequency, if you have flexible piers, and low seismic forces or lower seismic forces. Okay, so here we have a pile pier solution, and by putting here a transversal beam, you define the position of the plastic hinges that will be formed in a seism in the case of an earthquake, and it is in a position where you can achieve for some repair if needed. Okay, so here we have quite big sliding bearings, but on the contrary, we didn't need to use some special devices, which conducted to a simple and cheaper solution. But it's not always possible, of course. This is the example of two big viaducts that we did in the Lisbon area, one with almost 900 meters and the other one with 453 meters. And here we we thought it would be more interesting to have fully continuous decks, and that led us, and also we have small heights of the piers, so that led to here you can see the piers also with the pile pier solution, 1.5 diameter for the piles and the piers. And we had a lot of problems with also liquefaction on these valleys. And here you have to have a special care with the detailing of the reinforcement of the piers, of the piles, and also on the transversal beams where you have a lot of crossing of reinforcement. Nowadays we would use the BIM technologies to study that, but this was like 10 years ago or 12. So here we have a lot of 2D drawings to study these conflicts of the reinforcement, and we achieved this solution. Well, this is the drawing with all the equipment bearings that we used on one of those viaducts. For the abutments, we used viscous dampers to control the longitudinal displacements of the bridge during a case of an earthquake. And since the horizontal forces, either longitudinal and transversal, if we fix the bearings, would be enormous, we have freed the bearings of any blocking system. And for the transversal direction, we use just neoprene blocks, neoprene bearings put on this concrete block on the abutments, and with that we control the horizontal forces, transversal forces, and the longitudinal forces were transmitted or were lower because we use these viscous dampers. On the piers, I don't know if you can see it here, but we had here a zone with quite severe liquefaction problems, so the displacements on the transversal directions were bigger, so we had to free the bearings on the transversal direction and also on the longitudinal direction, because we have also the displacements from the creep and shrinkage and all temperatures. So we freed transversally the bearings here. We had only these two alignments fixed transversally because we had this fixed point here on the abutment and also here. So we defined the position of the bearings of or what you free for the bearings, depending on the soil conditions, the height of the piers, and so on, with simple solutions and conventional solutions. Another bridge is it's also in the highway between Lisbon and Algarve. We had here a main bridge with higher piers and higher spans, and here we have this mountain on the middle of the viaduct, which is the worst thing that you can have in a bridge when you have seismic when you are in a seismic zone. So these piers with irregular heights just inducts big forces on these piers and so
Pedro,
on. So,
disculpa, 10 minutos.
10 minutos?
Sí.
Muy bien, está bien. So for this, we try to use conventional bearings, but not possible. So we had to use some blocking systems in some piers and also some elastoplastic dissipators with steel hysteretic dampers, as you can see here on these bearings. This deforms and dissipates the energy, and the goal was to provide adequate and free displacements for the bridge, for the deck, for the service actions, permanent actions and temperatures, but blocking, dissipating or absorbing the seismic actions with these devices. This is an iterative, of course, process. You have to test. You have to test different configurations and to achieve the what do you think it's the best solution? Regarding the piers reinforcement, of course, if you have monolithic piers with the deck, you have higher moments on top and also on the bottom, mostly on the bottom of the piers. So you have to provide this less spacing for the stirrups near the foundation, near the deck, and the stirrups detailings are very important to achieve the adequate ductility that you are considering in your calculations. So, for example, in this pier, the idea is to provide each one on each two vertical bars that are hooked to provide enough ductility, and the configuration of your hooks also depend on the position, if you are on the bottom of the pier or on top of the pier. And this is really important to ensure that this is done on site, which is always a problem, because the contractors don't want to hook, because it's difficult. If it's hooked previously, it's difficult to assemble all this. And well, this is really key factor to have a good behavior on a case of an earthquake. Well, passing to another bridge, I was very pleased to see on this corridor we have two pictures of this bridge that Mr. Rito designed on the south of Portugal, the Jornada Bridge. And well, here he had like a big span, cable stayed span. This was built in the early 90s, so it's at that time we didn't have that so many special seismic devices to be used. So we thought, well, okay, we could. This is a cable stayed bridge with the two access viaducts, all fully continuous. So I have to control. Okay, I cannot control the displacements, but I want to use I don't want to use special seismic devices, and let's use the structure as a seismic device. So this is a fully suspension cable stayed bridge. So as you can see here, you don't have any transversal beam on or support of the deck. So the deck is fully suspended on the cables. What is that? This is a dissipator, a natural dissipator of the deck, of the masses. So that inducts very low natural frequency and lower seismic forces as well. So if you can, use your structure as a natural dissipator or damper device. Well, to finalize, I bring here 4 examples of tragic accidents on bridges due to earthquakes and what we can learn from this. This is on the Loma Prieta earthquake in California in '89. Well, this is clear, the shear failure, the bending failure, and it's clear that we have here a problem with reinforcement detailing, of course. Too less stirrups, too less confinement of the vertical bars. Well, this is just a simple and quick evaluation of this. Also in this Los Angeles earthquake, we also have, when you see a full span coming down and you see the piers on top, you have a problem with the connection of those two elements. They were not well connected. So of course, this is a very severe earthquake, but you have to take care with all these connections. You have to, if you are in a very high seismicity zone, maybe you have to have some robust devices like blocking the concrete blocks to block the decks to avoid the decks from falling. That's what you do in some countries, like in Algeria. They just demand that you have these concrete blocks to block transversally and longitudinally the decks to avoid them from falling. This is the Kobe earthquake, very severe earthquake, of course. But when you look at a bridge like this, quite heavy deck, one single pier. Of course, you want to have roads here passing from one side to the other, but having one single pier, what is this? This is an isostatic solution. So if it comes, it may fall, okay? And also here, this is a more recent earthquake in China. And when you look at so many decks falling, for sure, they had a fixed bearing in this side and a sliding bearing on that side, but the piers are on top. They didn't fall. They didn't. Sure, you don't have the best connection between the piers and the deck. Okay. Well, thank you very much, Ache. Thank you very much also the Portuguese Association of Structural Engineers, Luis Oliveira Santos, that invited me to come here. And muchas gracias por su atención. Perdón por hablar en inglés, pero mi castellano no es lo mejor.
Muito obrigada.